Hi everyone, this screencast is going to be a quick review of transformations, and we're going to be paying attention to a base function of 2 to the power of x. So I've set these sliders up here for a, b, c and d, and you'll note that a is a coefficient that multiplies the function, then 2 is our base. It doesn't have to be 2, by the way. I'm just choosing to use 2 as the base of the function. It could be any number for the base. B is the coefficient multiplying by x. Subtract c plus d. So let's check each one in turn. A is controlling the vertical dilation of the graph. So if I start playing around with the value of a, if I increase the value of a, we can see that the graph has been, it's a vertical change. Dilation is a word for stretching and compressing. So we have stretched the graph upwards. This point 0, 1, the y-intercept, if I just drop that point there onto my new graph, we can now see that whereas it used to be moving upwards by 1, we're now 5 times that. We're moving upwards by 5. On the other hand, this point over here on the original function had a y value of 2. Now, multiplying 2 times 5 means that all the way up there I'm now at a y value of 10 on the dilated function. I've literally taken the y value of 2 and multiplied by 5 to get a new y value of 10. The same thing works over here. Oh, missed. I tried to grab the point and I grabbed the label. Here we go. So if this point was about here on my original function, that's a y value of 1/2. 5 times 1/2 is, you guessed it, 2.5. So letter A literally just, in this case where A is a positive number, A is greater than 0, the translated or the transformed graph, this blue one, is upright just like the previous. Now let's move A back to 1. Now that's it, I've gone below 1. A is still a positive number, so it's still an upright graph, but whereas the original graph had a y value at this place of 1, it's now a y value of 1/2 times 1, or 1/2. At this point, the original graph had a y value of 2, and 2 times 1/2 gives the new y value of 1. Likewise, if I pick that spot where y equaled 4, the new one is y equals 2. But importantly, A is a positive number. It's still an upright graph. Interesting things happen when A drops to 0. As you would imagine, any y value multiplied by 0 is 0. So my graph has now just become a horizontal line. And now as I start to go negative, let me go to -1, then it's a reflection in the x-axis. Now, whereas the y value used to be +1, it's now -1. This y value used to be +2, it's now -2, and so on. Now that's a pure reflection, but of course, if A gets to be, say, -2, then I'm reflecting, but I'm also stretching. So what was +1 becomes -2. What was +2 becomes -4. So the value of A controls the vertical dilation, and dilation means it could be stretched or compressed depending on whether A is larger than 1 or less than 1. So fractional values compress, values larger than 1 stretch, and of course if A is positive or negative, that's where we have the graph being upright or inverted. So I'll put A back to 1 so that we aren't distracted. Now let's look at the effect that B has. B seems to be changing the horizontal values of the graph. So when B equals 5, let me take a look over here. The x-coordinate of this point was 1. Now the x-coordinate of this point is 1/5. The x-coordinate of this point was 2. The x-coordinate of the corresponding point is now 2/5, or 0.4. So it seems that B is doing a similar job to A, except in a horizontal sense. It is stretching the graph or compressing the graph in a horizontal way. Now, importantly again, when B is a positive number, either above or smaller than 1, but it's a positive number, the graph is upright, the same as the original base function. When B is a negative number, again, a fraction, negative fraction, or a negative number beyond -1, then the graph is now reflected in the y-axis. So the graph decreases as we read to the right. This blue graph now would be a good example of exponential decay, whereas the green one would be an example of exponential growth. So that's what B does. Let's put B back to 1 so that it isn't going to distract us. Now those ones are the more challenging ones. C is not actually changing the shape of the graph. The shape of this curve is identical. It's just that it's been horizontally moved. So at that point there, I had an x value of 1. I'm just going to make C equal to a nice simple number like 4. So horizontal value of 1, if I go 1, 2, 3, 4 steps to the right, I get to where the new graph is. X value of this is 2. 1, 2, 3, 4 steps to the right, I get to the new point. Where's another one? There's one. X value there is 3. 4 steps to the right, I get to the new graph. So C is quite straightforward. C shifts the graph without changing its shape. And that's what's called a translation. So we can shift to the right with positive values of C, and we can shift to the left with negative values of C. Please note that the formula is subtract C. So if C is a positive number, such as positive 5, then it turns out to be subtract positive 5. It looks like negative 5, but it's really that negative sign is part of the rule. And if C were negative 5, it's subtract negative 5. That would probably look like x plus 5 if we were to write it more neatly. So that's what C does. C controls the horizontal translation, just shifting to the left and right. And D has a similar effect in the vertical sense. Now there's something else moving along here with D. That red dotted line is the horizontal asymptote of this graph. The horizontal asymptote is the line where the graph approaches but never quite reaches. I know it looks like the graph is in line with there, but if we zoom right in, and I won't go too far, you can see there is a gap. The gap is getting smaller, and if we go across here, we'd have to zoom further, but there's still a gap. So asymptotes are limits. The graph never actually gets to the asymptote, even though it might look like it at this scale. If you zoom right in, you'll see that the graph is actually approaching but never quite getting there. So there's a quick rundown of what these transformations do. So there are 4 transformations, signified A, B, C, D. A controls the vertical dilation, B the horizontal dilation, and dilation means stretching or compressing. It changes the shape of the graph. C is a horizontal translation, that's just a shift. The graph shape doesn't alter. And D is the vertical translation. Now, of course, I did them one at a time, but there's nothing to say we have to do them one at a time. I could apply more than one of these at the same time. So we can control the entire graph with these types of transformations. Okay, that's a quick summary. The best way to learn how to do these sorts of things is to practice. There's nothing to stop you from building your own GeoGebra worksheet like this so that you can explore them for yourselves. Thanks for watching.